Okay, so we now know about alcohol dehydrations with sulfuric acid and heat, and they tend to work in a in essentially how we've learned about them. But it turns out that we've been kind of leaving a little piece of something out in chapters 7 and 8 and 9 up until this point, and what that's called is a carbocation rearrangement. So we know about the carbocation stabilities. Primary is the least stable, tertiary is the most stable, but it turns out that under certain circumstances, we can have something like a secondary carbocation turn into a tertiary carbocation throughout the course of a mechanism. And that's what we're going to talk about now. So essentially we have a secondary alcohol here, and that's going to react, as we've seen with sulfuric acid and heat. This is not a good leaving group in and of itself, so it's going to react with sulfuric acid to make the more stable acid, because hydroniumine is more stable than sulfuric acid. It's going to make a really good leaving group, this OH2+, and at this point, we have a secondary leaving group. We do not have a strong base or nucleophile, so this is going to lead to carbocation formation from that alcohol leaving. So at this point, we would have the secondary carbocation. So we'll write that in here, secondary carbocation. And without this part of our discussion, I would expect all of you to say, oh, this is going to be the product. We have beta hydrogens right here. They're going to be pulled off, and then the alkene will be formed right there to make that product. Well, it turns out that this product is not formed. If it is formed, it's formed in a very minor amount. So go ahead and cross that out from your course notes. The actual product of this reaction is this molecule here. So an alkene there with two different carbons on each side. Basically a tetrasubstituted alkene. So how do we get from here to there? So I think that this is a good part. I think that what I want you guys to think about is where the carbons are here and where they are here. So go ahead and pause the video for a minute and number your carbons. See if you can kind of try and figure out how the carbon framework had to rearrange to go from this species to that species. So you've done that. You you did it. Now you've unpaused the video, you're back. So how might we do this? Well, if we look at the product, we were going to name it, we'd probably look for the longest carbon chain, which is 4 carbons long. What's the longest carbon chain here? 1, 2, 3, 4 carbons long still. So let's number the remaining carbons, 5 and 6. There are 2 left. In the product, we'll just name them left to right, 5 and 6. And so where are those carbons on this molecule here? Well, carbon 5 is here. And then carbon 6 over here is attached to carbon 3, but here it's attached to carbon 2. So somehow carbon 6 and all of its hydrogens that it's connected to transferred from position 2 to position 3. So again, I want you to pause the video right now and think about a mechanistic flow of how you could draw that. And remember that mechanisms indicate the flow of electrons. So draw the electrons moving, not the carbon moving. Okay, you've done that. So carbon 6 has to move to position 3. So how's it going to do that? Again, it's a CH3. I'm just drawing that in. Essentially, this bond, the electrons in that bond are moving to add to position 3. So that's what this arrow shows, is that these electrons are pulling this CH3 species over to that position there. So what would that generate? Well, let's draw all the atoms that didn't move. So we have 1, 2, 3, 4. We have 5. And then where is 6? 6 is now off of carbon 3. And it doesn't really matter. At this point, 4 is on the top and 6 is on the bottom, which is different than up there. Which again, it doesn't matter at all. Like there's free rotation around there, so it shouldn't matter. But just to make it as clear as possible, I'm going to switch it up. So 2, 3, 4, 6. But again, it didn't matter if you had it one way or the other. It doesn't matter. So the question now becomes, where is the carbocation? So you've paused it. You found the carbocation. Where was it? Well, carbon 3 had a carbon, and for that carbon to have a formal charge of +1, it had to have a hydrogen. Did anything happen to that hydrogen? No, that hydrogen's still there. So in this species over here, that carbon still now it has 4 bonds. It had 3, so it was positively charged. Now it must be neutral. What about position 2? Position 2 is neutral, but it lost a carbon-carbon bond. So if we were to calculate formal charge for this carbon, it would be +1. So now the carbocation is on that position. So why did this thing happen? Why did that alkyl group move from position 2 to position 3? What was the point of that? All right, so take a minute and write down why you think this happened, because it should make sense. Okay, so we had a secondary carbocation here, and what species do we have over here? Over here we have a tertiary carbocation. So which of those species is more stable? The tertiary carbocation is more stable. So why would an alkyl shift like this happen? Why did that carbocation rearrange? It rearranged to make the molecule more stable. So like I said, in organic chemistry, we're looking for downhill reactions. This is certainly a downhill reaction because we've made a species that is more stable from something that is less stable. And also, I want to draw the name. I want to talk about the name carbocation rearrangement again. So the carbocation rearranged, it was secondary, now it's tertiary, but I don't like the name carbocation rearrangement. Why is that? Because the carbocation didn't technically rearrange. What rearranged was the alkyl group. Why does that matter? It matters because I've seen students push the positive charge instead of the carbon in the mechanism. And remember, we don't draw the flow of positive charges in a mechanism. We draw negative flow, so where electrons are moving. So carbocation rearrangement isn't really an accurate term. The carbocation isn't in a new position, but that carbocation is there because electrons moved to a new position. In this case, an alkyl group, a CH3. So this is what we had here. This tertiary carbocation, the more stable species. And how do we get from there to the product? Well, that kind of reverts back to our standard mechanism. We have our HOSO3 minus. It's got some electrons on that oxygen. They're going to come in here, grab that proton for that elimination reaction to occur, and that produces the product. So this is a new thing that we have to be thinking about when we are predicting products. It's really important. And the thing about this that complicates things is this goes all the way back to chapters 7 and 8. If we have a carbocation and a more stable carbocation can be formed by moving a hydrogen or a carbon, it's going to happen because we're going downhill in energy. Why didn't we talk about it in chapters 7 and 8? We wanted to keep things kind of, we're slowly building up the complexity, right? So to learn all about substitution, all about elimination at the same time as learning about these rearrangements, it makes things a little bit more complicated. So it's a little bit simpler to kind of build the new concepts in slowly. So that's why the book doesn't bring them up until this point, and that's why I don't bring them up until this point. But that is a thing that is applicable to all E1 or SN1 reactions as well. So it's not just alcohol reactions, it's also the reaction of alkyl halides. What was this called? This is called a 1,2 alkyl shift, and I have it on the course notes right there. 1,2 alkyl shift, a movement of an alkyl group from one carbon to an attached one. So this carbon, this alkyl group, moved from that carbon to the attached one. That's what a 1,2 alkyl shift is.